And just like that, we're in chapter 2. We're going to start with conservation of mass. This has a combustion reaction, which is going to give us a fuel of ethanol, CH3, CH2OH, plus oxygen makes CO2 and H2O. Don't worry that this is not balanced yet. We don't need it because we're not there. Combustion reaction of 46 grams of ethanol reacts with 96 grams of oxygen to make water and carbon dioxide. If 54 grams of water are produced, how much, oh, that should be over here. If 54 grams of water are produced, how much carbon dioxide will there be? Well, conservation of mass, we have reactants on one side, products on the other. If we have 142.0 grams of reactants, when those turn into new things, we're going to have 142.0 grams of products. If 54 of them are already accounted for, my carbon dioxide, the remainder has to be 88 grams. Whatever you start with, you have to finish with. No new matter can be created. Simple idea. Definite proportions, not a simple idea. These next two problems are going to be historical problems. They're really, really simple, but this is before scientists understood what elements and masses and molecules were, before they really had formulas for things. They just kind of described everything by words and masses. So we've got this thing, chloroform. It was a known chemical. They didn't know what it was, but they knew it was a chemical. And they knew that for every 12 grams of carbon in the chloroform, when they decomposed it, and they had methods to do this, we had 12 grams of carbon. They knew it was made up of carbon, chlorine, and hydrogen. And they always compare everything by masses. So if a second sample of chloroform had 30 grams of carbon, how much chlorine and how much hydrogen would it have? Well, we take it for granted, but they had to at some point prove that all chloroform was made up of the same stuff in the same definite proportion. So it's always going to be this carbon to chlorine to hydrogen ratio. So if the carbon here, just kind of a quick observation, 12 to 30 grams, that's 2.5 times bigger. If my chlorine is 2.5 times bigger, we're going to get 266 grams of chlorine. And if my hydrogen gets 2 times bigger, we're going to get 2.5 2 grams of hydrogen. So this gives them a little bit of predictive power. If they were able to find these things, the chlorine and the hydrogen in these predicted amounts, then they're like, hey, this 2.5 holds true all the time. And it's a really simple thought, but they were able to prove that, yes, every molecule of chloroform is made up of the same proportion of elements. Every chloroform is identical to every other chloroform in their chlorine, carbon, and hydrogen ratios. So simple thought there. But the problems are really kind of confusingly worded. But they're better than this one, the law of multiple proportions. Now you have to look at the strict definition of multiple proportions here. We're going to compare water and hydrogen peroxide. Now we have the benefit of looking at H2O and H2O2 in their formulas. They did not. Okay, so we're going to deconstruct this one a little bit backwards. We do have these masses, though. We get this mass ratio, and we're using their molar masses. They did not have these. But we can quickly see there's 2 grams of hydrogen for every 16 grams of oxygen for water. And peroxide had 2 grams of hydrogen for every 32 grams of oxygen. Grams of oxygen. So this is really important. This allows me to compare in a series water to hydrogen peroxide. the law of multiple proportions says for every 1 gram of the first element, what is its proportion to the second element? So if we reduce this hydrogen, we have 2 grams, ignoring sig figs. Let's reduce that to 1 gram. I have 1 gram of hydrogen to every 8 grams of oxygen. And the peroxide, let's reduce that one to 1 gram of hydrogen. Now I have 16 grams of oxygen. You do not have to do this math, by the way. We're just showing this series. What we're comparing then is we're comparing for every 1 gram of hydrogen. Now that we've standardized this, the hydrogens are the same. Now I'm able to look at the oxygens. It's 8 grams of oxygen there, 16 over there, which is a very nice and clean 1:2 ratio. What that allows us to show is that oxygen exists. Every oxygen is identical to every other oxygen. It has to be in this 8 or 16 ratio. There are these clean numbers here. One oxygen's not going to be 8 and the other one's going to be 5. They come in this clean ratio. It's a really simple thought. You need to be able to recognize a series of elements. So 2 elements made up in different proportions, just know that they will always come out to be, they will have similar mass ratios for their elements. In proportion to one another. So multiple proportion compares different elements in a series that combine in multiple different ways. You're not going to see that with ionic things because they don't do that, but covalent things, NO2, N2O2, N2O4, just different ways that, hey, nitrogen and oxygen might be able to combine. That would be a series that shows the law of multiple proportions. That one's tricky. There's not much we can do about it. You do not have to reproduce that math, though. The end of this here gets a lot easier because now we're just looking at the periodic table, and this part should be review from physical science or chemistry at the least. So given a symbol here, can we figure out how many protons, neutrons, and electrons are in the element? Element here in isotope notation. This first element here is going to be carbon. Here, down here, we've got a blank, we've got uranium, and then we have this unknown over here as well. In isotope notation, we've got an element, we've got the mass number on top, and we've got the atomic number here. So the atomic number is going to be the protons. So here my carbon has 6, this element has 92. So carbon has 6 protons. Oops, let's get that out. This element has 92. Well, 92 protons is how we identify it on the table, periodic table. This element is also uranium. So we can move that symbol over here to the notation. Well, the next element's also uranium, so it has 92 as well. What's different about that is going to be the mass. The first uranium has a mass of 235. And 92 of them are protons. The remainder are going to be the neutrons. So the neutrons here are only 143. The neutrons in my third one down there, my second uranium, it's going to be, I have 3 more neutrons that were given in this chart. It's going to be uranium-238 versus uranium-235. Different forms of uranium with different masses. This carbon up here has 14 with a mass, and 6 of them are protons, so the remaining 8 are going to be neutrons. Now to get to the electrons, for this particular chart, protons and electrons are going to be equal because they are neutral atoms. They have no charge. The next slide we're going to do some with ions that aren't like that. But if I have 6 protons, 6 electrons, 92 and 92, 92 and 92. And since we know this is a neutral atom, therefore if I have 25 electrons here, 25 protons, which gives me the element Mn. And I can put Mn over there with this number of 25. 55 is the mass, 25 of them are protons, there's a leftover of 30. So protons have a mass of 1, neutrons have a mass of 1, electrons have a mass of 0. Their charges And I should be careful how I write that, because protons have a charge of +1, neutrons have a charge of 0, and electrons have a charge of -1. But their masses, electrons don't have any mass, so they don't go into that mass number. And with this next one, we have ions now. You'll notice 3 of those have charges with them, and the 4th one will as well. So the charges, we look at the difference between the protons and the electrons to give me the charge. Protons are positive, electrons are negative. If I have more protons, I have a positive charge. If I have more electrons, I have a negative charge. The mass number is still protons and neutrons. So we can deconstruct these isotope notations. This sulfur here has 16 protons, given from its atomic number. Chlorine we can look up on the periodic table, has 17. The element with 56 is going to be barium, and that atomic number goes there. And the one with 24 is going to be chromium, and 24 is my protons there. So I kind of like to just do these in groups. Neutrons have to do with the mass. 32 minus 16 is still 16. 81 neutrons and 56 protons gives me a mass of 137. 20 plus 17 is going to give me 37, and then the bottom number is 17. And then this has a mass of 52, so take away 24, we get 28 neutrons there. Electrons, now this is different. Since my charge is -2, I have 2 extra electrons than protons. Since I have 16 protons, I need 18 to get 2 extra. This barium, I've got 56 and 54. I have more protons. How many more? 2 more. So this is going to be 2 plus. Okay, this one's -2. Now the last one says it's +7. So that's going to give me 24 protons. That means I have 7 extra protons. So I need to subtract down here to get 17 electrons. And the charge was given as +7. I skipped the chlorine, don't know why I did that. 17 protons there. If the charge is -1, there's always an implied 1 there. We have 18 electrons there as well. So you have to navigate charges, masses, protons, neutrons, and electrons. And the last example here is just kind of a periodic table game, if you know your way around the periodic table. The only metal in group 6A, and 6A is group 16. We kind of call those the A group, and then the transition metals, that 10 groups in the middle is the B group, but 16 will work fine. Those are full. If we start at the top there, those are nonmetals, and then there are metalloids until we get to the bottom at the element PO. But this is actually a little out of date, because just this summer, maybe last spring, the element below it, LV, was discovered, livermorium. You could include that. That is a metal in that group that has now been discovered. We are still discovering things. Alkali metal is in the same period as iodine. Period is a row, so it's in the same row as iodine. Alkali metals are group 1. This will be rubidium, Rb. And the last one, 2 atoms of this element, which is in the same period as magnesium, that's the same row as magnesium, combined with calcium ions to form a salt. Calcium has a +2 charge, so we need something that forms a -1 charge. These will be the halogens. The halogens in that row is going to be chlorine. So rubidium, polonium / livermorium, and chlorine.